Hey everyone. Today we'll be talking about how we will be able to predict credit card defaults using a machine learning approach. This presentation will be covering materials that will be presented by Antonio Recalde, Alejandro Marchini, myself, and Omar Sagu. As to the table of the contents, we'll start with the objectives of our study, then we'll dive into the dataset overview, after which we'll talk about the standard EDA practices we performed along with the data preparation for our models. Then we'll talk about the models that we selected for predicting credit card defaults. After which we'll talk about how we compare the performance of these models, and then we'll conclude. So moving on to the objectives of this project, our aim is to evaluate and compare the effectiveness of machine learning models in predicting credit card defaults while maintaining model interpretability for practical financial applications. The goal is to help financial institutions better manage risk exposure and maintain economic stability by developing accurate models that can identify potential defaults early while complying with regulatory requirements for transparent decision making. In terms of the dataset overview, our data comes from the UCI machine learning repository. The name of the dataset is the default of credit card clients. It contains 30,000 instances, of which 23,000 instances are for the non-default customers and 7,000 instances are for the default customers. The dataset has 23 features, including credit limit in dollars, gender, education, marital status, and other financial related information such as history of payment status, bill statements, and amount paid in a given month. In terms of the exploratory data analysis, we examined numerical features distributions using histogram and box plot. And then we observed significant right skewness in financial variables like bill amounts and payments. We also identified the presence of notable outliers, particularly in credit limit distributions and payment amounts. As to the start, to understand the features and their correlation, we performed a correlation matrix in which we found a strong correlation between sequential monthly features such as bill amounts and moderate correlation between payment status and default probability. This helped us inform our initial feature selection for the models. In terms of data preparation, we checked for the null values and did not find any. We also feature engineered our variables such that gender was mapped to binary values 0 for male and 1 for female, and then education level and marital status had values that were grouped into others. We also renamed some features for readability, such as X1 to credit limit, X5 to age, and X11 to April pay status. To manage the outliers, we implemented IQR, and we were able to cap about 167 outliers in credit limit, and on average about 2,000 to 3,000 outliers in payment-related features. For data normalization, we applied the min-max scaler to normalize numerical features between 0 and 1. This allowed us to capture ranges for credit limit that were between 10,000 and a million and age between 21 and 79. To address the class imbalance, as you see, our dataset had about 23% of default customers and 77% of non-default customers. We utilized k-means mode to synthesize realistic samples for the representative class, such that we were able to balance the class out. Moving to model overview and selection, I'll have Alex discuss about the models.
Thanks, Hassan. So before I jump into the models, I want to talk about how we'll be evaluating each one. So the metrics we'll be using are precision, recall, F1 score, and accuracy. Precision being the proportion of correctly predicted positive cases. So if we say a model has 50% precision, it means that out of all the predicted defaults, 50% of them were actually defaults, and recall being the proportion of actual positive cases correctly identified. So if we say it's 50% recall, of 100 recalls, 50 were correctly predicted. F1 score being the aggregate of the two, and accuracy being the percent of correctly predicted defaults and non-defaults in the test set. So I'll move on to XGBoost. So these were the numbers we were able to get with XGBoost. We're going to be focusing primarily on the number for defaults because that's what we're trying to predict. So for XGBoost, we had 60% precision, 44% recall, and a 51% F1 score. We learned some things about the features that led us to getting the model to these numbers. So the first model we trained used all the features available to us. The first thing we noticed is that the pace status features are by far the most important as scored by gain. Gain being the amount of knowledge that the model gains from the particular feature. We also noticed that the demographic features were lower on the gain score. We had been worried about the demographic features causing an unintentional bias in the model. And since they were low on gain, we decided to try training a model without the demographic features. And we found that they did not enhance predictions. So they're removed from the final model. For this new model that had the demographic features, we again scored the features by gain and still see the pace status features at the top. So we want to look at the features again another way. So we decided to use SHAP, which is Shapley additive explanations. So the first thing we noticed from gain and SHAP, and that we gathered from our intuition, is that the features from the more recent months before trying to predict the default are the most important. For SHAP, the most important is the September pace status. And we can see from the SHAP values that a high September pay status, which means they've missed multiple months of payments, led to a much higher risk of default. Where if you have a negative September pay status, meaning you've made many monthly payments in a row, you are flagged as much less risky for default. We also use SHAP to evaluate some of the interactions between the features. We had intuitions that the bill and payment features could have interactions, and the bill and credit limit features could have interactions. So first we looked at bill and payment, which ultimately amounts to a remaining balance feature that we derived by just subtracting the payment from the bill. We can see from the interaction that there isn't a strong correlation in either direction for remaining balance. So when we added the derived feature to the model, it didn't enhance the prediction. The relationship between bill and credit unit, credit limit is more interesting. We see that there is a harder cutoff where someone with a high bill but low credit limit is flagged as risky. So if you have a higher credit utilization, which is the feature we derived, that showed as more risky in this model. When we added the derived feature, it didn't improve prediction because we can see from the SHAP interaction that the model is already deriving that information from the two separate features. So we also use the SHAP threshold to try to improve performance. So we only included features in this model that met a certain level of SHAP importance. This is the list of features that met that threshold, but this didn't enhance performance over the previous model that just didn't include the demographics. So ultimately, the most successful model that we trained used just the credit limit feature and the billing payment and payment status data from the last 3 months before predicting default, going back to our intuition and what the SHAP value showed us that the more recent months were more important, and any month further in the past and any demographic information did not enhance the prediction. And these are the numbers that we got in our most successful XGBoost model. So next, I'll pass it off to Antonio to talk about naive Bayes.
Thank you. We chose naive Bayes as one of the models for our project, and while it performed comparably to XGBoost in predicting non-defaults with the same F1 score of 89%, it fell short when predicting the defaults, which is the primary focus of this project. Specifically, the F1 score for defaults was only 45%, highlighting that there are some limitations with this model. Our data set includes both categorical and numerical features, and each type requires a different naive-Bayes model. For numeric features such as age, credit limit, and payment amounts, we use Gaussian naive-Bayes, which assumes numeric data follows a normal distribution. For categorical features like gender, education level, and payment statuses, we use multinomial naive-Bayes, which is designed to handle discrete values. Additionally, since the dataset was imbalanced with far fewer defaults than non-defaults, we use k-means mode, and k-means mode oversamples the minority class by generating synthetic samples based on clustering, ensuring that the data is representative. So, well, this step helped improve the model's ability to predict defaults. Naive Bayes assumes that features are conditionally independent given given its target class, and to meet this assumption, we analyzed the numeric features using a correlation matrix and removed highly correlated values. And these highly correlated values could introduce like redundancy and violate the independence assumption of the naive Bayes. So similarly for the categorical features, we applied a chi-squared test to identify and eliminate the redundant variables. These processing steps were important in the end to aligning the data with the naive Bayes requirements for enhancing performance. To leverage the strengths of both Gaussian and multinomial by naive Bayes models that were implemented, then we also combined them into an ensemble using the voting classifier. This approach takes the predictions from both of the models and averages their probability using soft voting. By combining the models, we achieved better performance than running each model independently. As shown in the chart, the combined model achieved the highest accuracy, demonstrating how ensembling can enhance robustness and overall predictive power. Another attempt that we made in order to improve performance was to explore the insights that we gained from XGBoost, where the ratio between the September bill and the credit limit was highly important. So we created this as a variable and fed it to the naive Bayes. But in the end, ultimately, the results did not improve, and this was likely to the independence assumption, and which may not have be fully captured in these complex relationships. In conclusion, naive Bayes performed well in predicting non-defaults with a strong precision, recall, and F1 scores for the non-default class. However, it struggled to predict the defaults, achieving only a 35% recall and a 45% F1 score for the non-default class. This could be due to feature independence assumptions of naive Bayes, which oversimplifies the relationships between features. And like, for example, features like payment amounts, billing amounts, payment amounts and billing amounts are likely correlated in reality, but the model will assume that they're independent. Despite our use of k-means mode to address class imbalance, these limitations impacted the model's ability to identify patterns in the minority class in an effective manner. Overall, while naive Bayes has its strengths, it may not be the best model for predicting defaults with this data set. And now I'm going to pass it to Omar, who's going to talk about artificial neural networks.
Omar, you're on mute.
Oh, thank you for letting me know. I appreciate it. Oh, God. Okay. I can't even go back now. It's Thank you. I appreciate it. So we decided to use an artificial neural net for this task because credit card default prediction can involve identifying really complex nonlinear relationships between variables like payment history, credit utilization, and other factors. And artificial neural nets are particularly well suited for capturing those kinds of intricate patterns. And that makes them a really strong candidate for kind of solving this problem. So this slide shows a breakdown of the performance metrics of the artificial neural net. And just like the other models, we see a strong performance metric for the non-default performance. And the precision is around 88% with a recall higher up at 79% and an F1 score at around 83%. However, as mentioned, the default performance was the most important since that was kind of what we were looking at with our model. And this model performed fairly modestly compared to the other models. However, it did perform much higher with recall, and it had about a 60% default recall, whereas the other models had about 30% or 35%. However, the precision for the defaults was lower at around 45%, with an F1 score of 53%. You can see the weighted averages were kind of very similar to the other models as well, at 78% precision, 75% recall, and a 76% F1 score, respectively. So regarding the actual architecture of the artificial neural net, we decided, or I decided to use a very simple design for it. And there were only two hidden layers in the final model, and it achieved its optimal performance in roughly 25 epochs. And it was around maybe 20 to 30 epochs with a maximum of 50. And we also, just like Antonio with the naive Bayes model, used a voting classifier to combine predictions from the three other models using the soft voting as well, where it combined the probabilities. And the other models that we used were random forest and logistic regression. At the bottom, this is just a little visualization of what the voting classifier looked like. The artificial neural net had the highest weight to prioritize its ability to capture those complex patterns, whereas the random forest and logistic regression just kind of helped boost its performance. So regarding the actual training, one of the key challenges that we faced was handling the class imbalance in the actual training data. So to address this, we used k-means SMOTE, which was a resampling technique that combines clustering and synthetic oversampling to generate realistic examples of the minority class. And training this artificial neural net was relatively efficient. As mentioned, it converged in around 20 to 30 epochs. And this was thankfully because we implemented some safeguards to prevent overfitting, things like early stopping, which halts training when performance of the validation set stops improving, when it starts to plateau, and also including dropout layers, which regularize the model by randomly deactivating neurons during training. So the actual model training success during the training started around 67%, and then it increased to about 73%, which was very significant. And that indicates that there was a very stable validation accuracy throughout the training process. So yeah, as mentioned, the actual architecture of the artificial neural net was kept relatively simple with only two hidden layers. And this design allowed the model to balance computational efficiency and performance. So in conclusion, this model performed particularly well, just like the other models, when predicting non-defaults. And this is shown by the high precision recall and F1 scores. However, as mentioned, the more important class that we were looking for was the default performance. And when it came to that, it didn't perform as well as we would hoped. The recall itself was relatively high. It was higher than the other models at 60%, but it did have a much lower accuracy when actually trying to predict those payments than the other models. So thank you. I'm going to pass it back to Hassan to talk about the comparison of our models.
Thank you, Omar. So in terms of bringing this all together, how do the models compare with each other in terms of their accuracy, in terms of their area under the curve? So as we see in the first slide, we clearly see that XGBoost is the winner with 82% accuracy, but we also notice that Knife Base is pretty close, and then followed by ANN at 75%. When we look at the area under the curve, which helps distinguish between the default class and the non-default class, again, XGBoost leads by 77%, and then followed by ANN, and then Knife Base at the third place. So now let's look at how do these models compare when we look at the non-default class. Generally, every model is doing pretty well. When we look at precision, we see 87% with ANN leading the way, and then 86% for XGBoost and 84% for Knife Base. What's really astonishing is that for a simple model like Knife Base, we see a 94% recall, which is a very important metric because recall is actually looking at the proportion of actual positive cases. Therefore, Knife Base excels in finding those actual positive cases in the non-default class. But we also see that ANN is a close second here. XGBoost is a close second here, but followed by ANN is the third place. When we look at the F1 score, here we see that XGBoost and Knife Base are in the top spot, with ANN following the close second. So for default class, as we stated, every model performed really well. But when we switch to the default class, actually when we switch from the non-default class to the default class, we see quite a bit of a difference here. So when we look at Knife Base is the top performer for precision, and ANN is at the lowest point at 44%. In terms of predicting the default class, ANN did not do that well. However, when we look at the recall class, the story shifts. But ANN has a 60% score, and then followed by XGBoost and Knife Base. If we average everything out in terms of the F1 score, we see again XGBoost and ANN are in the top performing class. So in conclusion, we realized that XGBoost emerged as our recommended solution, achieving 82% accuracy while providing the transparency needed for regulatory compliance. It gives us the best balance of catching defaults while minimizing false alarms. While other models showed strength, particularly the ANN's ability to spot non-defaults and Knife-based strong recall, XGBoost's interpretability through SHAP analysis gives us the crucial advantage in explaining decisions to regulators and customers. Looking ahead, we would like to experiment with alternate data sets with variables like pay-to-income ratio and have data sets that have more default class instances, and also exploring combining XGBoost with ANN for stronger predictions. For the team participation slide, I mainly explored the dataset and performed the initial EDA analysis. Antonio Recalde worked on the multinomial and Gaussian knife-based algorithm. Alex Marchini worked on feature selection and XGBoost model implementation. And Umar Sagu worked on sequential artificial neural network model. Thank you for watching our presentation.